Multiple sclerosis, or MS, is a neurodegenerative disease which affects nearly 1 million people in the United States. It's notorious among neurologists for its difficulty to diagnose due to its wide range of symptoms. The McDonald criteria, the definitive MS diagnosis guideline, highlights white matter hyperintensity growth in MRI over time as the strongest sign of multiple sclerosis' presence. Taking such growth over time requires hours of tedious segmentation and area computation for hundreds of layers of a 3D scan. MRIs can take days to analyze for MS, and oftentimes multiple scans over time must be analyzed in order to come up with a definitive diagnosis. The American College of Radiology claims that in 2016, more than 60% of radiologists surveyed claimed to be fatigued or burned out from work. Radiologist burnout negatively impacts the diagnosis process, reducing quality of diagnosis. In fact, over 20% of MS patients in America are misdiagnosed, and misdiagnosis can lead to dangerous situations in which patients are not given proper treatment and can worsen in condition. As we are simply looking for substantial lesion volume increase over time to diagnose it, an AI can be perfectly applied to the task, saving radiologists hours of MRI analysis and comparison time. This is AIMS, or AIMS, an AI-based multiple sclerosis diagnosis tool. The system is based on an 8-thread mean and variance-based random forest classifier trained using labels across 5 heavy T2-weighted fluid-attenuated inversion recovery-based MRIs. And long sessions of calculating lesion volumes manually, AIMS is the perfect solution to bring much-needed relief for both the patients being misdiagnosed in the status quo and the burned-out radiologists who ought to be applying their efforts and expertise in analyzing more complex cases. To start off with pre-processing, we have to standardize the images that we feed into the program, and this can be done using a simple script that I made in ImageJ and Mango, which are two medical analysis applications that I used for the pre-processing aims. So the first step would be to extract the brain using the brain extraction tool, which is a Mango plugin, which is basically just removing the skull and other things that aren't brain matter. Afterwards, we can convert that 3D MRI Nifty file, which is unreadable by anything but an MRI reader, to an image hyperstack.tif file, which is easily interpretable by multiple sources. After that, we can downscale that image stack to a lower resolution to achieve faster training and run times, whilst also maintaining the resolution necessary to see lesions. Afterwards, we can just extract the relevant slices from with an increment of 2 to less than z dimension for faster run times. This is the final build of AIMS, and this is one of about, I'd say, let's look. 1, 2, 3, 4. All of these were the classifier versions that I had, and this is final classifier number 3. So, just looking real quick at this MRI. Usually MS lesions are in FLAIR are quite easy to spot, such as this. The hard part is actually getting the volume of this, as a radiologist will have to sit and either draw a region of interest box around this, or like have some sort of semi-automatic thing where they have to highlight this and then they have to do that. But essentially, they'd have to go through multiple of these every single day, all 140 slices of this, and look for individual ones. And oftentimes, even something as simple as spotting this could be quite difficult, or at least tedious and time-consuming. So, let's take a look at how AIMS does it. Let's just go over here and toggle the AIMS overlay. So, this is all done by the computer. The AI essentially looks at this, and it's been trained on 5 different MRIs to analyze lesions and detect all of them, even the smaller ones. Like, it's quite plausible that a radiologist would, especially having doing hundreds of these every day, would just select that and possibly miss that. You can see this picks that up. This picks up minute ones. That one, for instance, that is a lesion. It picks it up. But these things, these edges, they're naturally always lightened on MRI, but this learned to not identify those as lesion matter, which is a huge breakthrough. Moving on to this one, this is a separate one. This is a separate MRI, which has significantly fewer lesions on it, but we can see even the ones that it does have, the system is able to accurately pick it up with no false positives anywhere. And over here, you might wonder, isn't that a lesion? But it's learned how to look in 3D, and it sees that that's just matter that's dividing. That's not a lesion that's within the brain matter. That's just how the slice was cut. Moving on, here it detects a lesion, and that is indeed a lesion. It does not split. Moving on, we see minimal false positives. Over here, we do have a lesion, and it accurately predicts it. Over there, we have a lesion and it gets it, and nothing else, no false positives anywhere. And that is a success. Looking over here on this one, you can see it picks up most of the lesion matter here. This one's moderate. This person has more lesions than the last one, but significantly less than the first here. So on the left, you can see this is the regular FLAIR MRI overlaid with the results from the AI. Down here, you can see the AI's raw results, and over here we can see a radiologist's professional interpretation of those same results. And we can see that essentially The program was able to pick up everything that the radiologist picked up, yet even more small, obscure things that they may or may not have. Plus, some of these things are done in more detail than the radiologist's summary. So essentially, we can say that this program can compete at the same level that a radiologist can. Version of the final web app that I'm planning to make. So yeah, let's get into it. So essentially, this would act as a platform for a radiologist to sign in and upload their MRIs and essentially be able to track a patient's progress over time effectively and securely, um, as well as being able to utilize the actual AI in terms of its abilities to calculate volume of lesions for multiple scans instantly and even segment the image into lesion and non-lesion matter. So let's get started. So after signing in, a radiologist would be taken to a screen similar to this, on which they would have their patients on the left with the ability to add in more patients, and within each patient file, you would have their scans over time with the scan type listed, the date listed, and the AI's detected lesion volume also listed over time. So this radiologist would clearly see that this patient is getting more and more white matter lesions over time, and they could use this information to effectively make their diagnosis without having to segment every single one of these manually if they don't have the ability to. And below here, we can see patient data. They can be able to access the sex of the patient and the age, as well as their pre-existing conditions and clinical records, all to make their deliberation and diagnosis in one place. They would be able to upload new scans as a patient gets more, because multiple sclerosis oftentimes requires multiple scans over time to diagnose definitively, to make sure that the lesion in matter increase isn't happening due to anything else other than an autoimmune attack against myelin. So yeah, just to make sure that's not aging or anything. So they have to know what the rate of lesion matter it is. For example, if this, let's say that this radiologist wanted to check out the MRI, or maybe they have the ability to manually take a look at it and make sure that it's accurate, or they're just interested in where the major developments are happening, they could click on the MRI here, and it would bring up something like this, on which you'd see the title of the MRI and the date, and essentially you'd be able to scroll through these, like I showed in the previous one, the previous videos. You can scroll through these MRIs, and I hope to carry that over here. And after that, they'd be able to have a side-by-side comparison of, okay, so this lesion corresponds to this one, this corresponds to this to this, this to this, and be able to track where exactly these new lesions that they're seeing are happening. So in this clip, you can see that the program was able to achieve around a 93% accuracy rate, 93 to 94%, with a 66% to 33% training data to test data ratio. So essentially, I segmented, or rather drew, boundaries around maybe 50 to 100 lesions, or 50 to 100 images that were selected at random, and I labeled them as either lesion matter or non-lesion matter. So after that, that data was fed into the program, the classifier, and the classifier was able to report that by using 66% of the training data to train itself, and the rest of the 33% to test, the 66% data trained the program well enough to achieve a score of 93% accuracy on the remaining 33% of test data.